Explain the exploding gradient problem. As the vanishing gradient problem's opposite, the exploding gradient problem manifests itself during backpropagation when the cost functions gradients concerning weights in the early layers get abnormally large. Rapid weight shifts brought on by this disease may result in Shakey training. That the network might thus diverge or struggle to come up with the perfect solution. The increased gradient problem is frequently caused by inadequate network architecture, excessively high learning rates, and suboptimal weight initialization. The neural network's depth is depicted on the horizontal axis of the diagram, and the gradient value's magnitude is reflected on the vertical axis. As gradient values more as gradient values move farther into the network, they could expand exponentially, leading to a gradient explosion. The network may be prevented from arriving at an ideal solution by the escalation, which may lead to numerical overflow and weight modifications. It is possible to solve exploding gradient problem in many ways. Weight normalization. By controlling the weight magnitudes, weight normalization process aid in the maintenance of stability during training. Gradient chip clipping. To maintain stability and stop uncontrollably expanding gradients, gradient clipping involves setting a maximum limit on gradient sizes. Optimization algorithms. Stable training is increased by implementing alternate optimization strategies such as RMS prop or ADAM, which are less susceptible to the ballooning gradient issue. Weight regularization. By adding a plenty term to the cost function and encouraging smaller weights, weight regularization lessens the likelihood of gradient escalation. Learning rate adjustment. Weight updates can be slowed down by deliberately lowering the learning rate value, which lessens the likelihood of abnormally large gradients. Through the combination of these approaches, prac- practitioners may effectively mitigate the problems arising from explosive gradients, leading to a neural network training procedure that is both more stable and productive. Discuss the limitations of the simple RNN. The simple RNN neural networks has various drawbacks that may make it challenging to solve specific types of issues despite its benefits in particular applications. The following are these limitations. Vanishing gradient problem. The simple RNN is impacted by the vanishing gradient problem, which occurs when gradients are extremely small during backpropagation. The network finds it challenging to appropriately update its weight as a result of this issue. Short-term memory. Short-term memory intensive applications are better suited for simple RNN skills, as it finds it difficult to retain information across longer sequences. The gradient explosion problem, which happens when gradient become very huge, is another issue. This could cause the model's behavior to become unstable as weight updates with extremely large values. Computational expensive. It can be computationally uh, costly to train a simple RNN on long sequences, requiring a substantial investment of time and resources to train the model well. Capturing long-term dependencies is difficult. The capacity of simple RNN is identify long-term links within input sequences is limited. Because of this, it is less appropriate for tasks involving the modeling of dependencies. Explain how the LSTM neural network can provide powerful solutions to both gradient problems, vanishing and exploding, and address the limitations of the simple RNN neural network. An example of a RNN is the LSTM neural network, which effectively surmounts the limitations of the simple RNN neural network and offers robust solutions to the vanishing and exploding gradient problems. This is the diagram of the SRLSTM. To selectively recall or forget data from previous time steps, memory cells are useful design feature for long short-term memory. This selective retention of important information over multiple time steps helps to prevent the disappearing gradient issue. Moreover, gating mechanism built into LSTMs can adaptively regulate the information flow, averting the problem of gradient explosion. The network can discover long-term dependencies in the data thanks to the gating mechanism of LSTM, which is depicted in the graphic and enables the selective update and preservation of data over extended periods. The general design of LSTM successfully addresses the issue of disappearing and exploding gradients that are present in traditional RNN by ensuring a more stable gradient flow during backpropagation. Because of their sophisticated architecture, which includes memory cells, gating mechanisms, and the innate capacity to encode and stimulate long-term dependencies in sequential data, LSTMs perform better than simple RNN while processing sequential input RNN. LSTM with time series data. The neural network diagram shows three levels: the input layer, hidden layer, and output layer, totaling 40 neurons. Four neurons that receive data input signals make up the input layer. There are 16 neurons in the first hidden layer and 17 neurons in the second hidden layer, and one neuron which is responsible for producing the final output makes up the output layer. The importance of choosing the appropriate number of neurons to accomplish the desired neural network's performance is emphasized by the possibility that is uh, distributed of neurons in the hidden layers of many change based on the complexity of the problem and the data. An overview of the key variables used in the LMST model for time series forecasting is given in the following table. In the left side are the parameters and the right side are its values. So, in the shown figure, build, train, test, retrain, and forecast. This research aims to develop a RNN that utilizes the long short-term memory architecture to forecast stock values. 739 data points from past stock prices of applied common stock were used to train the model. Data preparation. Importing the required libraries including Pandas, NumPy, and Matplotlib was the first step. The applied common stock dataset, which had values for open price, high price, low price, close price, and volume, was loaded using pandas. I limited our research to only looking at the close attribute. The length of the input time series or the number of time steps used to estimate future values was then computed. To predict the next data point, the length was fixed at 148 historical data points during model testing. Next, the data set was split into two halves. 20% was put aside for testing and 80% for training. The minimum maximum scalar was used for normalizing to facilitate data processing. By standardizing the data to a common range in the important stage, the model was better able to identify patterns within the dataset. Model construction. The LSTM model was generated by specifying the number of features adding at LSTM layer with 40 LSTM cells, ReLU activation function, and written sequences is equals to true. The addition of a dropout layer stopped outfitting. The model was constructed using the Adam optimizer and the mean squared error loss function. The model summary, which was showed layers, output shapes, and trainable parameters, was created using the summary function. Modeling a neural network. The fit generator approach is used to train the model of the generated data generator. Producing batches of input-output pairs, a low mean squared error during the 75 training epochs is suggested by the loss, which drops from 0.2205 in epoch to 0.0049 in epoch 75. The Adam optimizer is used to update the model's weights at each epoch to minimize the loss function. LSTM, time series forecasting full input dataset processing. The minimum maximum scalar function from the scikit-learn module is used to pre-process the entire input dataset, DF. This stage ensures that every piece of the data falls into the same range. The normalized information is kept in a variable named norm underscore full underscore dt. The time series generator function of the Keras library is then used to generate a time series generator for forecasting. The input time series has 50 time steps to maintain consistency with previous settings. Next, the normalized whole data is subjected to time series generator, which has an input time series of the same length and batch size of 42. The time series generator does not divide data into training and testing sets. Instead, it uses all available data for prediction. The model may use the entire data set to make prediction thanks to the technique. After that, I defined a dataset called DF all, which includes the actual stock prices for applied optoelectronics in common stock and imported it with the forecasting period applied optoelectronics common stock. The closed column from the dataset was taken out and plotted. Next, the expected values were assigned to DFJS forecast column. The predicted and actual data were then displayed on the same plot using the plot method. Thus, the effective of LSTM model was demonstrated by a visual analysis of its performance is predicting the prices of applied optoelectronics common stock. The graphic showed how well the model could predict the overall trend in stock prices. In conclusion, this study illustrated how to create an LSTM model for stock price prediction by testing the model performance on a testing set and training it on historical closing prices of applied optoelectronics common stock. With a mean squared error of 0.0038 at epoch 75 on the training set, the model demonstrated excellent performance, but there's still potential for development with chances to look at other structures or optimization techniques to raise the e- efficacy of the model. Redesign the neural network. This is the diagram of the architecture of neural network with 15 neurons, and it consists of 5 input layers and 5 neurons in the input layer and 22 neurons in the hidden layer 1 and 22 neurons in the hidden layer 1 and 1 neuron in the outer output layer. The architecture, which consists of input layer of the data under examination, dictate how many neurons are present in each layer. The length of the input sequence and the batch size. The model is provided with a longer historic data sequence for learning with the time series. Input sequence is extended from 50 to 70 lengths. I experimented with the different batches size to find the optimal batch size for the training, and I found that 35 in the optimal batch size. And thereafter we perform the training variables and forecasting testing. Compare network performance. A notable dis discrepancy in the LSM neural network performance between Part 5 and Part 6 can be seen when examining its performance with various parameter values. This is how I compared the Part 5 and Part 6.